All right, let's look at now some factors in the sintering process that can control what happens during sintering. So I've talked about some of the overarching principles, but I want to sort of go through and talk about a variety of factors that often influence sintering. So again, as often I do, I want you to think about this before we talk about it. See if you can come up with what you think these factors are. So see if you can come up with what factors control, and I'm going to limit this to solid state sintering. And keep them, for this exercise at least, the goal is to obtain something that is theoretically dense, so a dense ceramic. So pause the video, jot down your answers, and see if what you came up with, and we'll compare as we go through the rest of the slides. All right, so I'm going to take you through some of the factors that influence sintering. Again, if you came up with something and it's not on the list, don't worry about it. There's a lot of things that influence sintering, so just try to think about how that can happen. So a big one, and this is something, for example, in lab, where we deal with sintering, this is often a variable or factor that we control quite easily, and that's the temperature. So temperature is obviously going to have a big factor, is going to be a big factor in sintering, because that controls the rate of atomic motion. And so that's important to us, the rate. But more importantly, temperature can also cause certain diffusion or mass transport mechanisms to be favored over others. And so we talked about surface diffusion, evaporation condensation, volume diffusion, plastic flow. We talked a lot about those last time. And so the big one here is going to be favoring bulk diffusion. The higher and higher temperature we get, the more and more we favor a bulk diffusion compared to others. And that bulk diffusion, or volume diffusion, is what caused a lot of the densification of those materials. So this one is kind of showing the change in length, so basically how close two particles are together in the change. So the greater the change, the more they're shrinking. And so at this higher temperature, T2 is higher than T1, we get more shrinkage than T1, and you can see it actually happens faster too. And that's because we're favoring volume or bulk diffusion, which favors densification. So as an illustration of this, let's look at diffusion plots versus temperature. So these are Arrhenius plots because it's log diffusion versus 1/T. And I put this up here because this is for silver, so it's not a ceramic, but the same principles apply. And so basically what I wanted to look at is the diffusion coefficient, or diffusivity D, for two types of mechanisms. So for volume, we see that it fits this line. So it has a slope of -192, and that's in terms of thousands. So basically 192,000 is the slope for volume diffusion. Whereas if we're looking at grain boundary diffusion, that has a slope of 84,500. So different slopes for different mechanisms, mass transport mechanisms. So what we see here, so this is an actual plot of silver diffusivity as a function of the temperature. So again, the Arrhenius plot. And what we see here is that instead of being linear, it's actually two slopes with a change in the middle. So what this means is at the lower temperature, and so the lower temperatures are to the right in this case, we have a slope that is lower. It's more similar to this grain boundary diffusion. And then at the higher temperature, in this case up here, we see that favors more of the volume diffusion. So basically at this temperature, so maybe at roughly 750, there's a crossover and a favoring of mechanism towards volume diffusion. So if we wanted to center silver and create that shrinkage, then we would want to make sure that we did it above this point so that we favor this bulk or volume diffusion as opposed to grain boundary diffusion. That's kind of the power of increasing temperature. So we often think just increase the temperature, that's what we're going for, but there's a reason behind why we're doing that. Okay, another factor that goes into densification is the uniformity of the green microstructure. So we can't just say everything's the same when it comes to the powder compact or the green microstructure. The more uniform it is, the better. And so what this plot's showing you is, again, percent theoretical density. So 100% is the best, obviously. And then this is a function of temperature. But we have two series. We have an as-received powder, so not much consideration goes into to that one. And then an agglomerate-free, so something that's been processed, so we don't have those big chunks. And so what this shows is that in all cases, this agglomerate-free particle, so more uniform powder means that we have a higher density at the end. So even though this is only the green state, that does influence the final density that we have. And so it really has a big effect at the lower temperatures. And so we want to make sure that that initial microstructure is super uniform. So we don't want those mixtures, and we don't want agglomerates like that. So that's an important aspect to bring up. Okay, so temperature, uniformity of the microstructure, and atmosphere. That's also an important condition. So when we talked about how we sinter, we talked about box furnaces and tube furnaces. And that's where I mentioned how we can control the atmosphere, right? So we can introduce different gases, control the pressure, all of those things. That's how we would do it. But let's look at what effect that can have. So this is a particular system. I believe this is an iron oxide. It's from the book, so you can kind of take a look at this exact system. But again, we're looking at shrinkage. We're looking at basically the change in length over initial length. So basically the higher the better in terms of densification. And what we see is that if we take a system and we look at air, and then we also look at air but mixtures of hydrochloric acid into that air, so we're changing the atmosphere, the more and more of that hydrochloric acid we put in, the less shrinkage that we're getting. So we're basically kind of contaminating the system such that if we introduce too much hydrochloric acid into the system, it actually causes coarsening. So basically that's the images that we see here to here. This is a coarsened system. This is the coarsened system in B. So basically the particles just got bigger, but they didn't densify. Whereas this is the fracture surface showing a very uniform microstructure, small particles, but very little porosity. It doesn't show up super great in the slide, but take a look in your book to see that. So changing the atmosphere can affect that condition. And the way that this can happen is the atmosphere can create the right defects. And what I mean by that is we've talked a lot about mass transport mechanisms. If you think way back to, just a simple metallic system, if we wanted an atom to move, we had to have a vacancy for that atom to move into. So the same thing here, when now we're looking at a ceramic, if we want an ion to move, we have to have the corresponding vacancy for that ion to move. And so certain systems are going to be limited by, for example, the anion vacancies or the cation vacancies. And so just like we saw with the Brouwer diagrams, certain atmospheres, low PO2, high PO2, can cause certain defects to occur. So maybe when we go to a low partial pressure of oxygen, that facilitates oxygen vacancies. and that may allow mass transport to happen faster. And so that's another way that you can think about this atmosphere and how it changes and causes the correct or the best defect to occur, which will aid in densification. All right. And again, this is the one that we've talked about multiple times now, but a lot of what we try to do to aid densification is to suppress grain growth, right? We want to, and the way we can do that is we can lower the grain boundary mobility. And so I showed this last time, but this is alumina again, undoped, and then we add magnesium oxide. This is something that when doped causes the grain boundary mobility to decrease, and it does so because the boundaries are kind of pinned by these impurities that are there. So that prevents grain growth or suppresses it, and that allows densification to happen, elimination of the pores before the grains grow and separate from the pores. Like we mentioned, that's a bad thing. Okay. So we mentioned the uniformity of the green microstructure, eliminating agglomerates. Well, the grain size distribution is also important. We want a very narrow grain size distribution, and another reason that is because that will eliminate any sort of abnormal grain growth where we can get these huge particles to grow, and that can cause additional stresses and cracks and pores to occur. And so we want it to be a very narrow distribution so everything grows at the same rate. Again, we talked about different applications. Sometimes we want these kind of large aspect ratio particles, but in this case, we're just talking about densification. Yeah, so this is where we have a small number of grains that grow much more rapidly than the rest of the microstructure. So again, this is a bad thing to occur. Okay, so I also wanted to mention the effect of particle size. Chances are, if you go out into the literature on ceramics and ceramic sintering, one of the big things that you're going to see is a push for smaller and smaller ceramic particle sizes to be used. And that is a result of the driving force. So the driving force for sintering is that removal of excess surface energy, right? You're trying to remove the fact that you have all these discrete ceramic particles with a lot of surface area, and we're trying to center them, bond them together, form grain boundaries so that we eliminate all of those free surfaces and instead bond and form grain boundaries. And then remove those grain boundaries and try to get as close to a single crystal as possible. So that's the driving force. So clearly, if we have more and more surface area, that's going to drive this reaction more and more. And so we can increase the driving force for sintering. So a lot of times what people do is they make nanoparticles of these ceramics, and they find that they can sinter at lower and lower temperatures and get the same result. And so this is obviously something that is good. We want to do this to increase the driving force. But I will mention that there are some negatives to this. And most of these kind of come from a processing point of view. So the more high surface to volume ratios that we have, the more dominant that we have electrostatic or surface forces that result. So electrostatic, that's basically if you've ever had particles that kind of, when you put them in a crucible or a weigh boat and they kind of fly all over the place, that's because these particles are so small that electronic forces on the surface cause them to be repulsed from other charged surfaces, and they kind of fly everywhere. And so that's obviously bad for processing. And that can also give us agglomeration. So it can give us clusters as well. However, those same surface forces, very small particles can make forming stable slurries, or another word for that would be colloid. You might see that term. it can make these slurries very stable because they're so small they don't separate out and fall to the bottom like we saw in sedimentation. And so making slurries, for example, through slip casting, can be enhanced by using nanoparticles. But again, agglomerates are bad for this. And so the processing, if we're doing some type of pressing technique for shaping and forming, can cause some issues there because they don't freely flow. And so there's processing challenges to nanoparticles, but there's also some advantages, obviously based on the driving force, and then the fact that we can use it in something like slip casting makes this very, very advantageous.